Imagine the entire universe as one enormous pie. Every star you have ever seen in the night sky, every planet, every moon, every cloud of gas floating between galaxies, every atom in your body, and in every living thing that has ever existed on Earth, all of it together makes up less than 5% of that pie. Not even a full slice, more like the thin layer of crust at the very edge. The rest of that pie, the overwhelming 95% of everything that exists, is made of things we cannot see, cannot touch, and have not yet fully figured out. About 27% of the universe is something called dark matter. Another 68% is something called dark energy. And here is the part that should genuinely stop you for a moment. We know these things exist. We have rock-solid evidence for both of them. We just do not know what they actually are. That is the story of this video. It is the story of how scientists figured out that the universe is mostly invisible, what the clues looked like, who found them, and what the latest experiments are telling us about the ultimate fate of everything. It is one of the greatest detective stories in the history of science, and it is still being solved right now. Let us start with dark matter, and let us start with a man who was largely ignored for decades after he found the first clue. In 1933, a Swiss astronomer named Fritz Zwicky was working at the California Institute of Technology, studying a massive collection of galaxies called the Coma Cluster. Zwicky measured how fast the individual galaxies inside the cluster were moving relative to each other, and what he found made no sense. The galaxies were moving so fast, at speeds of around 1,000 kilometers per second. Reserver Saner, Na Rai Bur Reader. Aber Amarisir and Ducking Dursel, Dashikuri, Our Dashir. That the gravity of all the visible stars and gas in the cluster combined should not have been nearly enough to hold them together. By rights, the whole cluster should have been flying apart. It was like watching a handful of rocks thrown into the air and noticing that instead of falling back down, they were all moving in completely random directions at enormous speeds, yet somehow staying together. The only way to explain it was if there was a huge amount of invisible mass hiding in the cluster, mass that was providing the extra gravity needed to keep everything bound. Zwicky called this invisible stuff Dunkel Materie, which is German for dark matter. His calculation suggested the cluster needed roughly 400 times more mass than the visible galaxies could provide. He published his findings in a Swiss physics journal in 1933, and almost nobody took it seriously. Part of the reason Zwicky was ignored was that his mass estimates were inflated by an incorrect value of the Hubble constant being used at the time, but his core insight was completely right. There was far more gravitating mass in that cluster than any telescope could see. The universe had a missing mass problem, and almost no one was paying attention. An early hint had actually appeared even earlier. In 1939, an American astronomer named Horace Babcock published measurements of how the Andromeda galaxy was rotating. What he found was strange. The outer regions of Andromeda were moving faster than they should have been if the mass of the galaxy was concentrated in the bright central regions, just like the mass of the solar system is concentrated in the sun. But like Zwicky's work, Babcock's result was not interpreted as evidence for invisible mass. It was noted, filed away, and largely forgotten. The discovery that finally forced the scientific world to take dark matter seriously came in the late 1960s and throughout the 1970s, driven by an astronomer named Vera Rubin and an instrument scientist named Kent Ford. Rubin and Ford used a specially designed instrument called an image tube spectrograph that Ford had built himself, and with it, they began measuring the rotation curves of spiral galaxies with a level of precision that had never been achieved before. A rotation curve is simply a graph showing how fast stars and gas are orbiting at different distances from the center of a galaxy. Here is what the rotation curve should look like if a galaxy's mass is concentrated in its bright central bulge. Think about our own solar system. Mercury, the innermost planet, orbits the Sun at about 47 kilometers per second. Neptune, the outermost planet, orbits at only about 5 kilometers per second. The planets on the outside move slower because almost all the solar system's mass is in the Sun at the center. The farther you get from the mass, the weaker the gravitational pull, and the slower things orbit. This is called Keplerian motion. If galaxies work the same way, with most of their mass in the bright central bulge, then the stars near the outer edges of the galaxy should orbit much more slowly than the stars near the center. But that is not what Rubin and Ford found, not even close. By Sir Cyber Meter Enver Nanoperseconteriar. When they measured the rotation speeds of stars and gas across the disk of the Andromeda Galaxy, and then across dozens of other spiral galaxies, the curves did not fall off the way Kepler's laws predicted. Instead, the rotation curves stayed flat. Stars on the outer edges of galaxies were orbiting just as fast as stars closer to the center, sometimes even faster. Galaxy after galaxy showed the same pattern. By the early 1980s, Rubin and Ford, joined by their colleague Norbert Thonard, had measured the rotation curves of more than 60 spiral galaxies, and every single one of them showed a flat rotation curve extending far beyond the visible edge. This was not a measurement error. It was the universe telling us something fundamental. There had to be a massive amount of invisible matter surrounding the entire visible disk of each galaxy, extending outward into a huge spherical cloud called a dark matter halo. The visible galaxy, all those beautiful spiral arms lit up with billions of stars, was just a small bright core embedded inside a far larger invisible structure made of dark matter. In her 1980 paper, Rubin stated plainly that the conclusion is inescapable that non-luminous matter exists beyond the optical galaxy. She also offered a beautifully honest perspective on how much of the universe this meant we were still missing, by saying that the ratio of dark to light matter in a spiral galaxy is about a factor of 10, and that this is probably a good number for the ratio of our ignorance to our knowledge. We are out of kindergarten, she said, but only in about 3rd grade. Rubin was right, and she deserved the Nobel Prize for this work. She never received it. The observatory now under construction in Chile bears her name in recognition of what she gave to science. At the same time Rubin and Ford were doing their work, 2 other independent lines of evidence were pointing to the same conclusion. In Estonia, an astronomer named John Einasto published a 1974 analysis showing that galaxies must be embedded in massive invisible coronas of matter. Also in the early 1970s, Jeremiah Ostraker and James Peebles at Princeton University ran computer simulations of galaxy disks and found something deeply troubling. A disk of stars, rotating without any surrounding dark halo, was violently unstable. Within a short time in the simulation, the disk would buckle, develop a strong bar shape, and fall apart entirely. But when they surrounded the disk with a massive dark halo, the disk became stable and maintained its beautiful spiral structure. Without a dark matter halo, galaxies as we know them simply could not exist for more than a fraction of their current ages. 4 completely independent lines of evidence were now all pointing to the same conclusion. Zwicky's cluster dynamics, Rubin and Ford's rotation curves, Einasto's halo analysis, and Ostraker and Peebles' stability simulations all demanded the same answer. Galaxies and galaxy clusters are surrounded by enormous invisible structures of matter that outweigh the visible stars by roughly a factor of 10. Dark matter was not a hypothesis anymore. It was a physical reality written in the motions of galaxies. Knowing that dark matter exists is one thing. Knowing what it actually is turned out to be a far harder problem. But before we get to the candidates and the experiments, let us look at 2 more spectacular pieces of evidence. The first is gravitational lensing. Einstein's theory of general relativity predicts that mass bends space, and that light traveling through bent space follows a curved path. This means that a massive object acts like a cosmic lens, bending and distorting light. By measuring how much background galaxies are distorted, astronomers can map the total mass distribution. When these mass maps are compared to the visible light maps, the dark matter halos show up clearly, far greater than the visible matter could account for. But the single most dramatic and direct demonstration of dark matter's existence came from the study of 2 galaxy clusters that had collided with each other roughly 150 million years ago, a system called the Bullet Cluster. When the 2 clusters collided, the galaxies passed through each other like 2 swarms of bees. The dark matter halos also passed straight through each other, but the hot gas clouds, being made of ordinary matter, smashed into each other and got left behind. The result was a clean, visible separation between the components. The hot gas, glowing brilliantly in X-rays, was piled up in the middle, but the majority of the mass was not in the middle with the gas. It was out on either side, coinciding with the galaxies. In a paper published in 2006, Douglas Clow and his team called their result a direct empirical proof of the existence of dark matter. If dark matter did not exist, there is no natural explanation. The bullet cluster is the smoking gun. On top of rotation curves, gravitational lensing, and the bullet cluster, 2 more lines of evidence confirm the dark matter picture. The first comes from the pattern of temperature fluctuations in the cosmic microwave background. The Planck satellite's precision measurements confirm that dark matter outweighs ordinary matter by a ratio of roughly 5-to-1. The second comes from Big Bang nucleosynthesis, the physics of how hydrogen and helium were cooked up in the first few minutes. The observed abundances of these light elements constrain how much ordinary matter could have existed. The majority of gravitating matter in the universe must be non-baryonic, meaning it is not made of protons and neutrons at all. So, what is it actually made of? The most widely discussed candidate for decades has been a class of particles called weakly interacting massive particles, or WIMPs. The basic idea is elegant. If dark matter particles interact through the weak nuclear force, then the natural processes of the early universe would have produced exactly the right amount of dark matter to match what we observe today. This is sometimes called the WIMP miracle. But despite enormous effort, no confirmed WIMP signal has ever been detected. The Lux Zeppelin experiment in South Dakota uses a tank containing 10 tons of ultra-pure liquid xenon buried deep underground, waiting for a tiny flash of light. A second candidate comes from a completely different direction. In 1977, physicists predicted the existence of a new, extremely light particle called the axion. It turns out that if axions exist, they could account for all the dark matter. Detecting axions is extraordinarily difficult because they are so light and interact so weakly with ordinary matter. The main detection strategy exploits the fact that axions can convert into photons in a strong magnetic field. So far, no detection has been made, though large sections of the theoretically interesting parameter space are being systematically covered for the first time. A third candidate is the sterile neutrino, a hypothetical heavy cousin of the ordinary neutrino that interacts even more weakly with matter. In 2014, two separate research groups reported a faint X-ray signal at 3.5 thousand electron volts coming from galaxy clusters and from the center of the Milky Way, which some researchers suggested could be the signature of sterile neutrino dark matter decaying into an X-ray photon. The claim generated enormous excitement, but subsequent observations with more sensitive instruments have neither confirmed nor conclusively ruled it out, leaving the 3.5 kilo electron volt line as one of the most tantalizing and unresolved anomalies in modern astrophysics. Primordial black holes, formed in the very early universe, represent yet another possibility. Decades of surveys have ruled out most mass ranges, but certain windows remain open, particularly for asteroid-mass primordial black holes. Beyond these candidates, some researchers have proposed modified versions like fuzzy dark matter, consisting of ultra-light particles with a quantum wavelength large enough to affect the structure of entire dwarf galaxies. Indirect detection experiments search for the products of dark matter particles annihilating in space. The Fermi Gamma Ray Space Telescope has detected a real excess near the galactic center, but its origin remains controversial. The IceCube Neutrino Observatory searches for neutrinos produced by dark matter in the Sun. The AMS-02 detector on the ISS measures cosmic ray positrons. All of these experiments have seen interesting signals, but none are universally accepted. The hunt continues, and while the experimental walls are closing in from multiple directions, the universe is stubbornly keeping its most fundamental secret. We know dark matter is real. We just do not know what it is yet, and that is one of the most exciting open questions in all of science. In the late 1990s, two teams of astronomers set out to answer what seemed like a straightforward question. The universe has been expanding since the Big Bang. Gravity pulls matter together. So the expansion should be slowing down over time, like a ball thrown upward that gradually decelerates under the pull of gravity. The question was simply how fast the expansion was slowing down, because knowing the deceleration rate would tell cosmologists how much matter was in the universe, and eventually whether gravity would one day bring the whole expansion to a halt and reverse it into a collapse. Both teams used a type of stellar explosion called a Type 1a supernova as their measuring tool. When a white dwarf star accretes enough material from a companion star to push its mass over about 1.4 times the mass of the Sun, Erdatzakir, Beintaker, Dandaranker, Namerfur, Daberektor, Dabereta. It undergoes a catastrophic thermonuclear explosion. This release of energy is remarkably consistent in peak brightness. By comparing how bright a distant supernova appears to how bright it actually is, astronomers have a reliable ruler stretching across the universe. The Supernova Cosmology Project and the High Z Supernova Search Team were both independently measuring distant supernova. Both teams expected to confirm the deceleration and measure it precisely. What they found instead shook the foundations of cosmology. The distant supernovae were fainter than expected. Not dramatically fainter, but measurably, undeniably fainter. In a decelerating universe, distant supernovae should be at a certain distance. These were farther. The universe was speeding up. The expansion of the universe was accelerating. In 2011, the leaders of both teams shared the Nobel Prize in Physics for this discovery. Think about how strange this is. Imagine throwing a ball up, and instead of falling back, it keeps going faster and faster, upward. In 1998, Michael Turner gave this mysterious component a name: dark energy. We needed something to call it while we figure it out. In 1917, Einstein introduced a mathematical constant he called lambda to keep the universe static. He later called it his greatest blunder, but that constant turns out to be the simplest description of what dark energy actually does. You can think of dark energy as a kind of rent charged on every cubic meter of the universe, with the bill growing as more space is created. Quantum field theory predicts a vacuum energy density 10 to the 120th power larger than what we measure, the worst prediction in history. Why it is so small, but not zero, is one of the deepest unsolved problems in all of physics. Steven Weinberg argued that if dark energy were larger, galaxies would never have formed. His prediction was remarkably prescient. Is dark energy a constant, or something like a field that evolves over time? Models of this kind are called quintessence. There is a more extreme possibility called phantom dark energy. It could lead to a catastrophic event called the Big Rip. Galaxy clusters pull apart, then solar systems, then planets. Earth would be torn apart 30 minutes before the end. The expansion rate of the universe comes out to two different values, depending on how you measure it. This is the Hubble tension. The 8% gap is too large to be a random fluctuation. It suggests our standard model is missing something fundamental. The Dark Energy Spectroscopic Instrument, or DESI, uses 5,000 fiber optic cables to map tens of millions of galaxies. DESI's recent data suggests dark energy may not be constant, but evolving, potentially stronger in the past. If dark energy weakens, it might allow gravity to reassert itself, leading to a big crunch, a total collapse of matter. Or the universe might grow colder and emptier in a big freeze, approaching absolute darkness and stillness. There's also vacuum decay, a bubble of true vacuum expanding at the speed of light, destroying everything instantly. Euclid, Rubin, and Roman are building an unprecedented picture of how dark energy has shaped the cosmos. 95% of reality is invisible, detectable only through its gravitational effects and its influence on space. We are still in third grade, but we are learning fast. Soon, we may finally know how the entire story of the cosmos is going to end.